So, you want to get into the deep sea mining business. The pitch sounds unbelievable. Drop robotic crawlers 4 kilometers beneath the Pacific Ocean, vacuum up billions of dollars in high purity battery metals lying loose on the seafloor, and watch the cash roll in. With the global transition toward electric vehicles and grid energy, storage driving unprecedented demand for nickel, cobalt, and copper, the ocean floor holds more of these critical metals than all terrestrial reserves on Earth combined. But building and operating a commercial deep-sea mining operation isn't like opening an open-pit gold mine in Nevada. It is a high-stakes, capital-devouring engineering nightmare where you are operating in pitch-black, freezing water under 400 atmospheres of crushing pressure, and a single broken riser pipe can drown hundreds of millions of dollars in seawater. To understand where the money is buried, you have to look at the abyssal plain known as the Clarion-Clipperton Zone, or CCZ. Spanning 4.5 million square kilometers of international waters between Hawaii and Mexico, this vast underwater desert sits between 4,000 and 5,500 meters below sea level. Resting on top of the soft abyssal sediment are trillions of polymetallic nodules. These potato-sized black rocks formed over millions of years as trace metals dissolved in seawater, slowly precipitated around tiny core fragments like shark teeth or basalt pebbles. A high-grade polymetallic nodule contains roughly 1.3% nickel, 1.1% copper, 0.2% cobalt, and nearly 27% manganese. Unlike land-based deposits that require clearing rainforests, blasting overburden, and digging miles of underground shafts, these nodules are simply sitting on the ocean floor waiting to be picked up. However, before you can drop a single piece of steel into the ocean, you have to cross a massive regulatory moat enforced by the International Seabed Authority, or ISA. Established under the United Nations Convention on the Law of the Sea, the ISA controls all mineral-related activities in international waters. Because no sovereign nation owns the ocean floor, private companies cannot simply claim territory. Instead, you must partner with a sponsoring state, often small island nations like Nauru, Kiribati, or Tonga, and apply for an exploration contract block spanning up to 75,000 square kilometers. Securing an exploration license requires paying millions of dollars in administrative fees, conducting years of baseline environmental impact assessments, and deploying oceanographic research vessels to map the seafloor using multi-beam bathymetric sonar. Once you prove economic viability and environmental compliance, you apply for a 20-year commercial exploitation contract, agreeing to pay production royalties and environmental funds to the ISA. Once you have your legal license, you face the central technical challenge. How do you physically extract millions of tons of heavy rocks from 4,000 meters underwater? The answer requires a 3-part offshore engineering architecture consisting of a surface production vessel, tracked seafloor collectors, and a vertical riser lift system. At the center of your ocean footprint sits the surface production vessel, or SPV. This is not a standard cargo ship. It is an ultra-heavy, dynamic positioning offshore vessel measuring over 200 meters in length, costing $400 million to $700 million to construct or convert. Equipped with DP3 dynamic positioning thrusters connected to real-time satellite navigation, the vessel uses computer-controlled propulsion to maintain its exact position above the seafloor collector despite howling winds, massive swells, and strong ocean currents. Inside the hull sits a massive moon pool, a central vertical opening through the ship, housing heavy-lift gantry cranes, pipe handling systems, and industrial dewatering plants. Directly below the ship, resting on the seabed, are your tracked seafloor collectors. These 90-ton remote-controlled robotic vehicles look like massive steel bulldozers riding on heavy rubberized hydraulic treads. Powered by multi-megawatt electric umbilical cables dropped from the surface vessel, the collector crawls across the abyssal silt at speeds of 1 to 2 knots. As it moves, forward hydraulic water jets create a low-pressure vortex that lifts the loose nodules off the seabed without digging deep into the underlying clay. Internal mechanical acoustic sensors and high-definition cameras guide the vehicle, while continuous hydraulic suction draws the nodules into a central crushing mechanism that breaks large rocks down to manageable 50-millimeter chunks. Now comes the hardest engineering feat in the offshore industry, getting those crushed rocks 4,000 meters up to the surface. To accomplish this, engineers install a vertical riser pipe system made of high-strength, flexible steel riser pipes suspended through the ship's moon pool. To lift the heavy nodule in water slurry up a 4-kilometer vertical pipe, operators use either submerged positive displacement hydraulic pumps installed along the riser line or an airlift injection system. In an airlift system, massive high-pressure compressors on the surface vessel inject compressed air into the riser pipe at a depth of 1,500 meters. As the compressed air bubbles rise and expand, they dramatically reduce the overall density of the fluid inside the pipe, creating a powerful vacuum effect that sucks the slurry up from the ocean floor at speeds exceeding 5 meters per second. When the slurry arrives at the surface production vessel, it empties into an onboard industrial dewatering plant. Vibrating screen separators and hydrocyclones instantly strip the seawater and fine silt from the solid nodules. The dry nodules drop onto conveyor belts, feeding the ship's bulk storage holds, while the separated seawater and fine sediment are piped back down through a secondary return pipe to a depth of 1,500 meters. Discharging the return water deep below the photic zone is critical to prevent surface turbidity plumes that could block sunlight, disrupt phytoplankton, or choke pelagic marine life. Every 5 to 7 days, a 60,000 deadweight ton Handymax bulk carrier docks alongside the surface production vessel. Floating hydraulic transfer hoses offload thousands of tons of dewatered nodules from the SPV to the bulk carrier, which then voyages across the Pacific to onshore metallurgical processing hubs in Asia or North America. Onshore, raw polymetallic nodules cannot be fed directly into standard battery manufacturing plants. They must undergo specialized pyrometallurgical or hydrometallurgical processing. In a typical pyrometallurgical circuit, nodules are dried in rotary kilns and smelted in rotary kiln, electric furnaces at temperatures exceeding 1400 degrees Celsius. This initial smelting stage separates the iron and manganese into a slag while producing a concentrated nickel-copper-cobalt matte. Secondary high-pressure acid leaching, or HPAL, uses hot sulfuric acid to dissolve the matte, allowing solvent extraction circuits to isolate pure battery-grade nickel sulfate and cobalt sulfate. Now, let's talk about the raw numbers and unit economics that make this high-stakes venture worth the risk. Building out an integrated deep-sea mining operation requires a staggering upfront capital expenditure of $1.8 billion to $2.5 billion. This covers $400 million to $700 million for the surface production vessel, $150 million for seafloor collectors and umbilical systems, $200 million for the vertical riser lift assembly, and over $1 billion to construct or retrofit an onshore metallurgical processing facility. However, once operational, the ongoing operating expenses, or OPEX, reveal why mining executives are fighting for CCZ contracts. A commercial deep-sea mining vessel targets a collection rate of 3 million wet metric tons of polymetallic nodules per year, which translates to roughly 2.1 million dry metric tons after dewatering. Your daily operating expenses at sea are substantial. Fuel for the vessel's dynamic positioning engines costs $80,000 to $120,000 per day. Specialized offshore marine crews, ROV pilots, and engineers add $50,000 per day, and continuous mechanical maintenance and umbilical replacement add $40,000 per day. Offshore transshipment and ocean freight to Asia cost roughly $25 per dry ton of nodule, while onshore metallurgical smelting and refining cost $120 per dry ton. Adding up all sea-based extraction, shipping, and onshore refining costs yields a total operational cost of $220 to $280 per dry metric ton of processed nodule. On the revenue side, one dry metric ton of high-grade CCZ nodule contains approximately 27 pounds of nickel, 23 pounds of copper, 4.5 pounds of cobalt, and 540 pounds of manganese. At conservative long-term commodity prices, the total recovered metal value inside a single dry ton exceeds $500 to $650. Multiply that by 2.1 million dry tons, and a single surface vessel operation generates gross annual revenues of $1.1 billion to $1.3 billion. Subtracting your total operational expenses of $500 to $600 million leaves you with $500 million to $700 million in annual operating profit, or EBITDA. That represents a net operating margin between 45 and 55%, allowing investors to fully pay back their initial $2 billion capital build-out in under 4 years. Yet, despite these staggering financial returns, deep-sea mining remains one of the most volatile industries on Earth. Environmental non-governmental organizations and several sovereign nations are aggressively lobbying the International Seabed Authority for a moratorium or outright ban, citing potential destruction of fragile benthic ecosystems, acoustic disruption to marine mammals, and long-term sediment plume dispersion. Operationally, if a heavy storm snaps your 4-kilometer riser pipe or a 70-ton collector bogs down in deep abyssal clay, your entire multi-billion-dollar operation grinds to a halt while burning through hundreds of thousands of dollars a day in idle vessel charter rates. Ultimately, deep-sea mining is the ultimate high-risk, high-reward frontier of modern industrial extraction. By combining deep-water offshore oil technology, heavy robotic subsea engineering, and high-margin battery metal refining, operators are turning the deepest, most remote ocean plains on Earth into an unstoppable multi-billion-dollar cash flow engine